So, we've been talking about what is monitoring, why do you monitor, what are the questions, how do we make sure the data we're collecting is corrected in a high quality manner, and how do we turn data information. I'm here to kind of talk about, okay, what does that information mean in the realm of water quality? So, in my world, or in the water board world, we're a regulatory agency. We try to protect water quality. And how we do that, where we garner our authority is from the Porter Cologne Act. It's part of the Water Code, and that really tasks the state with protecting beneficial uses for the enjoyment of the people of the state, and that they should attain the highest water quality possible, considering all demands. It's kind of a legal speak for saying that there are economic value that might trump our uses for enjoyment, and then lastly, to protect water from degradation. So this is kind of where we derive our power and our authority. It's primarily in the 13,000 of the Water Code. How we do that is by using water quality standards. That's a term that's derived from the Federal Clean Water Act, and they are defined as provisions that consist of beneficial uses of a water of the U.S. and then a criteria that's used to protect those uses. In California, we say water quality objectives rather than criteria, and we use beneficial uses of waters defined in our water quality control plans. We have two versions of that. The regions each have a basin plan, which outlines all their waters in their basin as they define them, and they define the beneficial uses, both existing and potential. And then on a statewide basis, we have things like the ocean plan, and there's also an inland surface water, enclosed bays and estuaries plan that's kind of in forms of development that should be coming out with the toxicity provisions if that goes through. So what's a beneficial use? Think swimming, or what are the uses of your water that you think of? Do we swim in it? We drink it? We fish out of it? This is, there's terms that we use. For swimming, we use Rec 1, or it's a shorthand for water contact recreation. Fishing is usually defined by COM, or the consumption of fish. Aquatic life support, that's a big one. It's defined as warm or cold water species. And that one comes up a lot because generally speaking, the objectives they use to support those lives are more sensitive than our own. So you'll see a lot of listings based on aquatic life support because of the acute concentrations and chronic concentrations of pollutants are at a much lower level that tend to affect us as humans. So there's the beneficial uses, and there are the objectives. Again, that's called criteria and EPA speak, and those are designed to protect those uses of the water body. And then further, there's implementation programs. Okay, we got the objectives, we got the uses. How do we implement programs to achieve those objectives? And for California, we include both surface and groundwater for each water body. So water quality objective, what makes up that? So those are the limits of a pollutant or pollution for the regional protection of beneficial uses. They come in two forms: numeric, those are the straightforward ones, where it's a concentration of a pollutant, think 5 micrograms of copper or something like that. Those are pretty straightforward, outlined, easier to enforce. And then there's kind of a narrative where these paragraphs that kind of describe a general requirement for a water or a prohibition. I'll show some examples of those. So here's an example of a numeric one. So at a minimum, the average annual dissolved oxygen of all waters has to be greater than 7 milligrams per liter and never less than 5 milligrams per liter. So that's pretty straightforward. You're gathering DO data. You have samples across a year. You can take a average of that. If it's less than 7, then there's something wrong there. You're not protecting that beneficial use. This is aquatic life. And then if there's anything less than 5, even if your average is at 7 or greater, if you ever have fallen below 5, that's also an indication that something's going wrong there, and that use isn't being fully protected, so something should be done. There are also site-specific water quality objectives. So generally speaking, water quality objectives apply to a use, says it's protecting that use. But in certain cases, water bodies are naturally different. They stand out. One example that I kind of put in here was that if you have a hot spring that's going to be naturally occurring up in the mountains or the foothills, that's going to naturally have levels of boron and other metals in that water just because it's simply being fed by a specific type of source. So in those places, a significant work is being put in to say, okay, this water naturally has these things at a high level, so we're going to set our objective at a higher level. Generally speaking, they're at a higher level than what would be a normal water quality objective, and those only apply to that specific water body. And again, those require a whole rigorous analysis, UAA, use attainability analysis, and a whole federal process for approval. Last example, a narrative water quality objective. So this is where it gets a little bit complicated. So here's a couple of examples. Water shall not contain floating materials, blah, 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 in concentrations that cause nuisance or adversely affect beneficial uses. Now, it's that last part. What does that mean? And the same with another example that's commonly used. No toxic substances in toxic amounts. That's used all the time, and it's like, well, what does that mean? Because my opinion of a adversely affected beneficial use or a nuisance might be one piece of trash. Yours might be, I'm okay with 5. So it's kind of, it leaves it up to interpretation, and that becomes difficult in the realm of kind of assessing beneficial use support. So how we do that within the assessment arena is we use evaluation guidelines to help interpret those narrative objectives. It's generally in a non-regulatory context, but again, the 303 list is very powerful, and if you are listed on the 303D list, a TMDL is likely to follow, or a more rigorous study is there to kind of delve in deeper to see if there is a problem and better characterize it. So we use these evaluation guidelines to help translate those narratives into numerics. The most common evaluation guidelines that we use, EPA's 304A, or National Recommended Criteria. You probably see those from time to time where EPA will come out with a recommended criteria for aquatic life and human health. They will do that because it's a little bit easier than going through the whole process of updating the CTR or the National Toxics Rule, but they're basically as close to an objective as you can get. They're based on several studies based on chronic toxicity, acute toxicity, and we can use those to help address a lot of the pollutants like pesticides or contaminants of emerging concern. They'll be on this list that we can use we can say that no toxics at toxic amounts, and say we have PFOA or another newer kind of pesticide that we don't have an objective for. We can find it maybe on that criteria and say, okay, well, this indicates that it's toxic at this amount, so we'll use that as our assessment numeric. There's other effects range lows or effects range mediums that are kind of done. Mostly those occur in academic studies and recommendations, so we use those to help kind of translate those type of narrative objectives. So here's my predecessor spent his better part of his career developing this water quality goals database, and this is intended to kind of provide all of those in one spot. You can go to this page and put in a constituent like copper or something less common than that, and search for it, and it'll come up with all sorts of different evaluation guidelines and objectives that you can kind of choose from when trying to find an evaluation guideline. I will say that it's been a couple of years since it's been updated. That's not for lack of trying, but Elisa Holmes in Division of Water Quality assures me that it's going to be updated sometime soon. But she's also listed as a contact for that, so she can help answer those questions as she's updating it. That's, I believe, that's all I've got. Any questions? That was a lot. Okay. Thanks.
All right, so we heard a lot about standards, and at times they can be a little bit complicated, maybe not super digestible from someone from the public or even high-level management. It just doesn't translate well. So I'm going to talk a little bit about water quality indices, and just to get a sense of comfort level knowledge in the room, how many of you have worked with a water quality index? How many of you have calculated an index? Oh, all right. Okay. So this is going to be pretty high level. I'm not going to go into a lot of detail about how to calculate indices, but what I will do is just provide a high level overview of what an index is. I think we hear that term a lot, but it's not always defined. So I'll do that today. And then I'll talk a little bit about how they're used, what are some of the limitations, and then go through probably pretty quickly a few examples. So just generally speaking, a water quality index is a way to summarize and simplify what can be pretty complex water quality data. So we heard a little bit with Nick's presentation about, and we saw earlier with David, and I don't see you, these very complex data sets that we might have. But it's not super easy just to say like, oh yeah, my water body's doing good based off of this huge data set. And so an index is a calculation to put it into more understandable terms. So it's usually some range of 0 to 1 or 0 to 100, which means it's not doing so well or it's in excellent condition. Okay. So a few different uses. I think the primary use is it's a communication tool. So taking some of that complex water quality data and turning it into information. We've heard a lot about that today. It's also a really good way to have a scientific, rigorous method that you can use to support decision making. So typically we're pulling together large data sets, we're optimizing that use, maximizing that use, and as you'll see in some of the examples, it's a strong communication tool that's scientifically defensible to help prioritize some of our management actions. That could be at the local level, from water board's perspective, it varies, which kind of gets at that scalable piece. So indexes can be applied locally for reach scale or within a smaller area, all the way up to statewide or nationwide levels. And then another really great value of these indices is they provide a consistent way of interpreting this data across the state. So I think with my water board hat on, it's really useful to use some of these indices so that I'm looking at a specific watershed, scoring that the same way that my colleague may, or maybe somebody at Department of Water Resources. So we're kind of looking through the same lens at these watersheds so we can prioritize those protection actions. So with that, though, they can be very overly generalized, right? So you're pulling in all of these complex data sets, and most of the time we have subject matter experts that maybe I'm a biologist, and so to me, that one variable that's looking at bugs and habitat is most important to me, but maybe there's a chemist in the group that they really want to look at nitrogen and phosphorus. So in that way, these indices can be weighted towards different variables that aren't telling the whole story necessarily. So yeah, they're not telling the whole story. And we heard this yesterday during the symposium that we usually want this one tool to rule all, similar with these indices. So you can't have one index that rules all. They're, like I said earlier, they're at different scales. They're looking at different variables. You can pull different indices in and kind of tell that bigger picture story, but we can't just say one to rule them all. And then they're often limited in terms of time and space. So if you have monitoring data that's a little off within a specific reach, or it falls within a time frame that doesn't quite represent the data or those conditions, that can skew your index too. Okay, so just to run through a few examples, how many of you are familiar with the Canadian Water Quality Index? All right, a couple of you. So this is Bev's saying, yep, she's Canadian, she knows. So this index is I'm kind of the forefather of a lot of the indices that are used specifically for chemistry. So I feel like icons have been really trending in all of these presentations. But so that little icon up there, I tried to categorize how these indices are used. So this guy is primarily looking at chemistry. It's not looking at biology, which we'll talk about in a second. But essentially what this index does is it has this calculation. It's looking at the scope, frequency, and amplitude, and then it gives you some score of 0 to 100. And then those scores are then divided or ranked into 5 different categories. So anywhere from poor to excellent, with excellent being it's meeting these thresholds, Nick talked about that, or these water quality guidelines, consistently meeting those over time, whereas poor, it's not doing so hot, we're not meeting those standards or those guidelines. So the Central Coast, Melissa in the room, I'm sure is very familiar with this, with the Central Coast Water Board. So they have a dashboard. There's actually, I don't know how many, but there's several indices in there. Again, there's not one single index to rule them all. They all kind of tell a different story. And so what I'm showing here is just a basic water quality index. And this one, again, it's modified from that Canadian Council of the Environment Water Quality Index, and it compares it to a threshold of concern for each analyte at each sample site. And then it looks at the proportion of samples that are exceeding that threshold and the magnitude of each measurement relative to the threshold, which is similar to the Canadian index, just in slightly different terms. And again, we have that same kind of categorization. So within this watershed, reds representing sites that are not doing very well, with the bright green being excellent conditions or good conditions. So something like this is much more, it's a stronger tool to communicate how this specific watershed or this region is doing versus a bunch of numbers or a pH of 7. What does that really mean to somebody, you know? And so this is taking all that information, putting it into digestible, understandable terms. So kind of moving them more into biological indices, the CSCI, the California Stream Condition Index, this guy we use at SWAMP for our bioassessment program. This is used statewide, and it's a scoring tool that is taking that complex habitat and stream data. We look at bugs, the benthic macroinvertebrates, that are living in a stream, and we use that as an overall measure of health. So it's debatable, but some people might lean more towards looking at biology as the true indication of how that stream is doing rather than chemistry or physical habitat or any of those alone. And so CSCI does a really good job at looking at those organisms living in that dynamic ecosystem, and then it wraps it up into this index to say something about those conditions. I'm not sure how familiar everybody is with this index. I'll just briefly say that essentially what this index does is it's calculated by looking at, you go out, you do your field protocol, check out how the habitat's doing, what bugs are living in there, and then that's compared to what you would expect in that system. So it's, they model and look at, it's essentially predicting based on the climate and based on geology, what kind of bugs would I expect to be here, and then the closer you are to 1, the better shape you're in. The closer to 0, not so good, or we say very likely altered. Along those same lines, we have a physical habitat index. So this is a newer one. I've included the reference here that we have on our SWAMP webpage if you want to check it out. And this, again, this is a multi-metric index, and it's looking at physical habitat conditions in streams. So this has been really what we're looking to do moving forward in assessing our watershed water body conditions is, I think the water boards have historically looked to chemistry as our answer to how things are doing. Now we're incorporating the CSCI score, which I just talked about, using that index, and also this physical habitat index to support those decisions. So if you have, maybe the chemistry doesn't look so great, but we've got great physical habitat, great biological condition according to this index, how would we list that water body and how could that support that decision? Also, these indices are really helpful for how we would prioritize restoration sites or areas that we might want to protect. So the chemistry only tells you so much, biology, habitat. We can use that information to then say, all right, this is high quality water body, the bugs are doing great, habitat's intact. Let's prioritize that area for protection. Or for those of you that are with local watershed groups, I know a lot of the work is restoration work and grant funding. So these indices are a powerful tool to use that as support to say, we're gonna put all of our effort into this area, these indices support that. Scientifically rigorous, although, yes, oversimplified. And then the last one I just wanted to touch on is some work through the Healthy Watersheds Partnership, which is one of the working groups of the Monitoring Council. And we've talked a little bit about chemistry, a little bit about biology and physical habitat. And so what this assessment or this index does, it's multiple indices, and it pulls information looking at those key watershed functions and processes. So I have listed here just 6 of those watershed attributes that that go into calculating this condition index. So we're looking at overall landscape condition, habitat, hydrology, geomorph, water quality, and biological condition. And so the output, there's just one example here, but it's this map is showing the relative watershed conditions statewide. And so this is a really powerful tool. Again, it's statewide and it's very high level, but a powerful tool to say, here's how our watersheds are doing relative to one another throughout the state, looking at all of these complex attributes, chemistry, physical habitat, and biology. And there's more information on this on our webpage, which I probably should have put in here, but I forgot to. Well, thank you all.